Okay, now we're going to continue that same concept of the circular diffraction. The problem says a light of wavelength is the same wavelength that we had before, 580 nanometers, is coming from a binary star system. If the aperture of a telescope is 15 meters and the stars are 600 light years away, so we're assuming here that you have a binary star system, they're both 600 light years away from us, and it says 1 light year is 63,000 AUs. It says A, what is the minimum resolving angle of the telescope? So in other words, how far away, at minimum, how far away should the two stars be in terms of radians? How far apart should they be as measured from the Earth in order for us to resolve them as being two binary stars? So that's called the minimum resolving angle. And then B, what is the minimum distance between the stars to distinguish them apart from each other in units of AU? Okay, so let's see what we're talking about here. From the previous video, we saw that the distance of the first central maximum circle is equal to what? Y1 was equal to 1.22 lambda d over A, right? So we're going to use that same concept here, and we're extending it a bit further. Here's what we're saying. If we have two objects, right? So we have a certain opening here. So let's say in this case we have a telescope, right? We have a telescope, and then here is the opening of the telescope, right? Each object's light will go through the opening of the telescope and create a diffraction pattern in the back of the telescope, right? So, for example, let's focus on one of the stars now. Let's just focus on this. The light will go through, and then it'll have a pattern here. Let's just draw like a screen here in the back, and you'll have a pattern like this, right? Of course, the star is much farther away, but I'm just trying to fit it here into the size of the board. So now let's draw this star a little bit bigger, like this. So now we can say that these are similar triangles. The distance from the center of this to the center of the star, from the end of the star to the center of the circle, to the center of the opening. And then we can draw this distance from the opening of the telescope to the back of the telescope. And we could have also done this about our eye. This could have been our cornea, and then this would have been our retina. And so the concept is the same. And then from here to here, these are similar triangles, right? So in the previous problem, we were concentrating on how big is the image, right? We were saying the image of that is equal to y1 is 1.22 lambda d over A. The A was how big this was, right? That's the A. The lambda was the wavelength. The d was the distance to the screen. And then the y1 was the radius of that circular bright fringe. In this kind of a problem, you now have to talk about the object that you're looking at. This would be we can call this y2, the size of the actual object you're looking at, the star, or it could be some light source. And then this could be d2. And then this could be d1, right? Well, by symmetry of similar triangles, we can argue y2 divided by d2 is equal to y1 over d1. Okay, so therefore, that would be equal to what? y1 divided by d, that would be 1.22 lambda over A, right? And what is that equal to? That's equal to this angle theta. Remember, we said we're assuming the angle theta is small, so we have sine of theta is approximately equal to tangent of theta, which is approximately equal to the theta measured in radians. Okay, so tangent of theta is y2 over d2, and the theta itself is also the same. So therefore, this is equal to theta. So this is called the resolving angle. So now here is the concept. So now if we draw the diffraction pattern of both stars together, it will look like this. You have two stars, and you have the opening of the telescope or your eye, and then you have the tube, and you have the back of the telescope, and then this one forms a pattern here, and then this one forms a pattern here. So let's say the worst possible scenario that you want just before they start to overlap is that the top of one diffraction pattern, the central diffraction pattern, is touching the bottom of the top central diffraction pattern. And now you could barely distinguish them as being two separate objects, right? So now draw a line from the center of the telescope to the middle of one diffraction pattern and to the middle of the other. And I can say this is the angle, the resolution angle. And then I can make a similar triangle to this one, and I can say this is theta. This theta is equal. This is the minimum angle that I want them to be close to each other. If they're any closer than that, the two patterns will overlap. I will not be able to distinguish them apart, okay? So these are similar triangles. So y minimum is what? 1.22 lambda over A, as we showed earlier. So then I could put now 1.22 lambda is equal to 580 nanometer, and in this case the telescope is 15 meters. Now we can answer the question, why do we want telescopes with bigger and bigger aperture? Well, the bigger and the bigger aperture it is, the minimum angle is closer together. That means the two stars can approach each other, right? So the bigger the aperture of the telescope, the higher resolving power it has, because the angle minimum, theta minimum, goes smaller. The two stars can get closer and the patterns will still not be touching each other. So the bigger this is, the smaller the theta minimum is, which is good for you, okay? So we can say 10 to the 9th nanometers is equal to 1 meter. Cancel that, nanometers cancels. And what are the units? Well, everything canceled. The units comes out radians. Radians. Notice here we only used the wavelength of the light, and we only used the aperture of the telescope. Okay? So at minimum, the two stars have to be 4.7173 times 10 to the minus 8 radians. Now, if we answer question B asked, what is the minimum distance between the stars to distinguish them apart? They were how many? They were 600 light years away. The distance was 600 light years from us. Well, we can say the angle is equal to what? That's equal to the distance between them. We can call that D2, right? Whereas this one we call D1, the distance between the images here. And then this one is the distance from us, okay, of the two stars. So we can call that capital D2, 600 light years. So D2 over 600 light years, okay? So how far apart should they be? So we multiply this number by 600. So what is that equal to? So since this one was equal to that, D2 came out to be 0.000028,304 light years. But each light year is 63,000 AUs. What's an AU? It's the distance between the Earth and the Sun. That one astronomical unit. So if we multiply that by 63,000, 1.78 AU. Okay? This is an approximate number. One light year, approximately 63,000 AU. So the distance between them, the two, approximately again, it comes out to be 1.78 AU. Okay? So if we had a 15-meter telescope and there were two stars 600 light years away, they would have to be at minimum 1.78 AU away from each other, which is about twice the distance between us and the sun. That's how far apart they would have to be in order for us to look through the telescope and say, oh yeah, there's a binary star system over there, okay? So now you can see how to use this. If they were farther apart, what would happen? Let's say they were 1,200 light years away from us. Well, then they would have to be twice as far away. 3.56 AUs. If they're twice as far away, they would have to be twice as far apart from each other in order for us to distinguish them apart, okay? So you can see how to use this concept now. Now you know how to apply this circular diffraction equation to such things as astronomical viewing and telescopes, okay? Thank you very much.